Hi everybody, I'm Luca Costantin, a research fellow at the Astrobiology Center in Madrid, Spain. And in this talk, I will present my latest result about the morphological evolution of massive disk galaxies. And in particular, I will focus on the assembly history of the bulge component. So I will discuss how we identify that a relevant fraction of old and very compact bulges can be considered as red-nugget relics hidden in massive disk galaxies. During this talk, I will show you how good photometric data add an important piece of information in characterizing the assembly history of galaxies, even though we all know that a lot of information is enclosed in their spectra. So I will start to put my work into context by showing a cartoon of the evolutionary path of a galaxy takes in the two-phase formation scenario. During the first phase, we have the formation of a compact system, which is usually observed at redshift higher than 2. During the second phase, on the right part of the cartoon, this system, usually called red-nugget, could evolve unperturbed until today or grow inside and end up as a local early-type galaxy. In this scenario, both relic galaxies and the core of early-type galaxies have the key to trace the physical mechanism which govern the galaxy evolution at the redshift. But you may be wondering at this point, this is a bulge conference, so where are the bulges? Well, we recently proposed that also late-type galaxies represent a natural path of evolution of red nuggets, and some of them could die in their center. But let's take a step back. So we can ask ourselves what simulation predicts. Here, I'm showing several snapshots of two illustrious galaxies that I've taken from Snyder and collaborator 2015 paper. There are many more examples in different simulations, I assure you. And it can be seen in this simulation that a concentrated stellar structure can acquire an extended stellar disk as it evolves. In the example, galaxies evolve from right to left, and it can be seen that a disk starts to form around kind of spheroidal component around redshift 2, and it is totally in place by redshift 1. So simulation already predict that high redshift spheroids can acquire a stellar disk, but what do observations tell us? So after discussing the context in which we're moving around, I will jump into the analysis of our 91 massive disk galaxies. These are the galaxies more massive, the 10 to the 10 solar massing from redshift 0.1 to redshift 1. They are in good snort and they can be modeled with a bulge and a disk component. In this plot, you can appreciate how the morphology of some of these galaxies changes as a function of the galaxy's mass and as a function of the bulge to total mass ratio. Moreover, you can also see the different distribution of bulge to total and masses of our bulges and disks to better understand the composition of our sample. But before better knowing the physical property of these galaxies, let me introduce SHARS. SHARS is a state-of-the-art imaging survey, and it is led by Pablo Perez Gonzalez, and it targets the Gussnall field and provides multi-filter deep photometry in 25 bands, covering the wavelength range from 0.5 to 0.95 microns. And it is the excellent data quality that we have in our hand, and in particular, the spectral resolution it provides that results fundamental to study the stellar population properties of bulges and disks in our galaxy, with a novel technique of spectrophotometric decomposition. But let's continue a step at a time. So indeed, we combine shared spectral resolution with the spatial resolution that only HST images can provide. So it's time for me to introduce the galaxy AT522, which kindly accepted to be with us today. It is a galaxy of 10 to the 11 solar masses at redshift 0.46, and you can appreciate how it looks like in HST and shared imaging. Again, HST images will help us to properly characterize the structure of each galaxy and in particular the bulge and the disk, while shared images will provide the spectral resolution to derive the stellar population properties of each component. But at this point, you may be wondering how the spectrophotometric decomposition I mentioned earlier works. So let's have a look at our galaxies, and we start with the measured photometry in the bluest HST filter and move along the spectrum until we reach 1.6 micron. And we also add the K-band from WIRCAM. But we have more, I told you this. So let's have a look how Sharp's data will improve the characterization of the galaxy spectral energy distribution. So here it is. At this moment, we can model the set with our favorite library and recipe to characterize stellar population properties and star formation. But again, we can do way more. So here I'm showing the photometric decomposition of the galaxy at 1.6 micron. Taking advantage of HST amazing spatial resolution, we use the gas 2D algorithm and model the galaxy to be the sum of a bulge and a disk. So as you can see from the radial profile in the main panel. But we can do this on all HST images, but again, we can push this a step further. And we can transfer the structural information to shared images. So we photometrically decomposing the galaxies in all filters, as you can appreciate in these three examples. In particular, you can see how the bulge to this light, it changes as a function of wavelength. So I think it's now getting clear what we are going and which is the potential of this technique. So we will have the spectral energy distribution of each individual bulge and each individual disk of our galaxies. And we can model them to properly characterize the assembly history and the stellar population properties of our bulges. So we model the star formation history of each component with a decline delayed exponential law. And I have listed here some other ingredients that we use for the set fitting. You can find all the details about the fitting and the modeling, as well the information about the spectrophotometric decomposition in my works. But jumping into the analysis, the first property that I will discuss is the mass-weighted formation redshift. Since our galaxies are observed at different redshift, this is the redshift which corresponds to the mass-weighted age. And it can be interpreted as the time at which the bulge forms. If you focus on the red point in this plot, or better, on the red histogram, you can see that bulges form in two ways. So they have a bimodal distribution of mass-weighted formation redshift because 33% of our bulges were formed at redshift higher than 3, with a median value of 6.2, while 67% of them were formed at redshift lower than 3, with a median value of 1.3. So having identified these two waves of bulge formation, we label the older bulges as first wave bulges and the younger bulges as second wave bulges. But let me tell you more about these bulges, and in particular about the first wave bulges. As you can see here, bulges share the same position as early type galaxies in the mass size relation, which is the red dashed line. So in particular, we find that some of them fall in the region of very compact system. Here they are. And we can see the same behavior in this other plot. So on the y-axis, we have the mass surface density of our bulges, which is an indicator of their compactness. And again, we see that the degree of compactness correlates with the stellar mass, and that the most massive and compact bulges are the ones that form first in the universe. Here they are. So we identify these first wave bulges as relic of the red-nugget population. Here, I'm showing both the mass assembly history on the left and the star formation history on the right of our bulges, dividing them in first wave in purple colors and second wave in orange colors. The plot on the left is telling us at which rate bulges are assembling their mass, and symbols go from smaller to bigger, defining when a bulge accretes 10 to 90% of its mass. So the tracks go from left to right as the age of the universe increases. Complementary, the plot on the right is telling us the bulge median star formation rate at a particular instant of their lives. So from this plot, the takeaway message is that first wave bulges form very fast at high redshift from a very intense episode of star formation. Until now, you may realize that I haven't talked about the disk component, but I want just to mention one important detail. Here I'm showing the age difference on the y-axis between each bulge and disk of our galaxies. And this is plotted as a function of the bulge to total mass ratio. Purple symbols are again for first wave bulges, while orange symbols stand for second wave bulges. And for all points that are above the gray shadow region, the bulge component is older than its disk. Thus, this plot is showing that the majority of our galaxy form inside out, being the bulge component older than its disk, and that the bulge mass regulates the timing of the disk growth. In particular, we see that first wave bulges take on average almost 5 gigayears in acquiring a stellar disk. Thus, we propose that first wave bulges form due to violent disk instabilities, which causes a compaction event at very high redshift, the same event that is probably responsible to shade the population of blue nuggets. Then they rapidly quench on timescale of 100 mega years, resembling red-nugget population, which is commonly observed at redshift 2. But they acquire stellar disk later on, around redshift 1, and reside in the center of a massive disk galaxies as a relic of their red-nugget freeze. To summarize a bit, this is the cartoon of the evolutionary path we propose for first and second wave bulges. They are labeled, the first wave bulges, as fast-track spheroids, which again, this is because they assemble their mass very rapidly in the first phase of the universe, right? Then they go through a compaction, a quiescent phase, and after that, they acquire their disk and are observed as a massive disk galaxy by redshift 1. And I have no time to enter in the details neither of second wave bulges nor the assembly history of the disk component, which, as I told you, happen around redshift 1 for both types of bulges, but I invite you to look for the entire discussion in my works. Before concluding, I have a final remark about a new project which will come out soon, and this is Omega, Origin of the Morphological Evolution of Galaxies. And this project aims at studying high redshift galaxies and their morphological properties. And getting ready for JWST NIRCam and mid observation, we produced images of about 25,000 galaxies from illustrious TNG50. So the first data release of both synthetic images and NIRCam mock observation is already available for everybody. And I will leave you the link to retrieve it. And if you are interested in exploiting this dataset, just have a look for your favorite high redshift bulge in TNG50. Summarizing, we found that bulges form in two waves, and that first wave bulges represent a fundamental missing piece of the two-phase formation scenario, being red-nugget relics, which acquire a stellar disk at a later stage of their life. So I will leave you with my conclusion, and I will thank you for your attention. See you at the conference.